Hi everyone, I hope everybody's doing well out there. One of the most common questions I've been asked recently is how do I get started? What are the basics of building a small scale solar system just so I can power maybe a freezer like I do in my other video, or a small refrigerator, or my TV and a DVD player to get through some tough times, a little bit of entertainment. I have designed and built several of those, and so I thought I would take time in this video to actually draw out and explain the components within a small scale 12 volt solar system, as well as do a case study on a small system, how to properly design it, how to properly size it. So the one I'm going to do my case study on later in the video is actually a design very, very similar to the freezer solar system on the wall behind me that operates my chest freezer 24/7. So it does allow for use of a freezer, a small fridge, any of those small appliances, keeps your phones, your laptops charged up. So like I said, not enough to run everything in your house, but enough to limp by and let you have a few creature comforts if you do experience the brownouts, blackouts, long-term outages. So let's get right to it. So, as always with my channel, I'm a little more substance over style. So you'll notice, those of you with sharp eyes will notice I'm using a construction pencil that's been used many times. And it's red and it sticks out against the background, so that's why I'm using it. So we'll go ahead and start from the beginning of the process. This is the sun. It may look like a California raisin, but I'm not really known for my artwork, as you can see, but I try my best. Yeah, this is the sun. These are photons. This is your solar panel. This is what actually produces the electrical current or the electricity that's going to power the whole system. So the photons from the sun rain down and they hit the solar panel. The solar panel is generally made up of two layers of silicone with a junction in the middle. So what happens is the photons hit the first layer, they knock electrons loose. The electrons jump over to the other side, and then as they try to get back, they're caught in the junction, and the electrons flow down the junction and out, and that's what creates your current coming out. Now the characteristics of the panel is that if you lay it out in the light, the voltage is going to remain relatively stable. So if it's a 12 volt panel, it'll actually put out about 18 volts, give or take, but whether it's cloudy or sunny, it's going to remain right near that 18 volts. What fluctuates is the amperage coming out. So the voltage will remain relatively stable, your amperage will change, and that's going to change the amount of watts that are coming out of it. And the reason for that is because watts equal volts times amps. So the voltage will remain the same, the amperage will fluctuate depending on how much actual light is hitting this and how bright and intense the light is. So that's going to cause your wattage to fluctuate. You'll have two conductors coming out. You'll have a positive and a negative coming out of the solar panel. I'm going to mention this one time, I always put fuses on my positive conductors. That's for safety, for the components and for the actual wiring. So anytime you see a fuse, I'm not going to explain it, you know what that's for. So the next component in the system is a charge controller. I'm not going to go into a whole lot of detail. There's generally two types, and I'm going to give you the pros and cons to them in a minute. But the function of the charge controller, it's kind of the brains of the system, and what it does is it manages the energy coming in to appropriately charge the battery. You can either give it manual instructions how to charge it. Some of them are self-sensing, so they'll determine what kind of battery you have when it hooks it up, and it'll create a charging profile for you. So like I said, what this does is it takes the energy coming in and it charges the battery the most efficient way possible. Now you have PWM controllers and MPPT controllers. The PWM is a little older technology. It's simple on-off. It'll release energy for a certain period of time, it'll stop. It'll measure the voltage and how the battery's doing, and then it may turn back on. It'll pulse back on for a little while, turn off, pulse back on, turn off. Whatever it takes to charge the battery to the maximum potential. It's generally lower cost, lower efficiency. The next is MPPT. Now this is variable. It maximizes the charging potential. It's generally higher cost and higher efficiency. This is the type you want to use if you are in a cloudy environment. It maximizes the amount of power coming in, and it's constantly charging it to the maximum potential. The PWM turns it on and off, on and off, on and off. The MPPT constantly changes it and maximizes the power that you have coming in. So that's, like I said, better for cloudy environments or where you need to charge faster at a higher efficiency. So now we arrive at the battery. We've created our energy. The charge controller knows what's coming in, knows what type of battery we have, and the battery is where your power is stored for use. It's a direct current, and you want to make sure you have a deep cycle battery. Regular car batteries, that type of thing won't work. They're not engineered to actually handle the constant draining of the battery, charging of the battery, draining of the battery, charging of the battery. Now, there's different types of batteries, right? There's lead acid, sealed lead acid, AGM or absorbent glass mat, and then there's life PO4 or lithium batteries. I'm not going to go into a lot of the details, but the lead acid, sealed lead acid, and absorbent glass mat, those are a little older technology. You can only discharge those so far before you damage them. Life PO4 batteries are the newest chemistry, and they allow a deeper discharge and they allow a lot more cycles. You get more return on your investment by using those. Over the long run, they're actually cheaper than these other types. But if you're constrained by a budget, these will work. They just generally won't last as long over time. So now our solar panels created energy. Our charge controller has taken that energy, knows what type of battery you have, and has charged it to the best of its capabilities. And now you have DC energy stored in your battery. The problem is most appliances around your house run on AC. So what you need to do is convert the DC to AC voltage so you can just plug in your appliances and they'll work, right? So what we need is the inverter. Now the inverter takes the DC inputs from the battery, inverts it from DC to AC, and then it allows you to plug directly into the inverter any appliances or whatever that you want to use around your house. So there's two things that are important to remember with your inverter. If you have a 12 volt battery, you have to make sure your inverter is rated for 12 volts DC. It can't be a 24 volt, can't be a 48 volt. If your battery is 12 volts, your inverter has to be 12 volts. So the second thing with the inverter is it's rated by its wattage output. So if you're running 500 watts of appliances on the AC side, from your house, say you got a lamp at 100 watts, you got a TV at 200 watts, and say you have an Xbox or something, right? So what you want to do is if they all add up to 500 watts, your inverter has to be rated for at least that 500 watts. Okay, so let's do a real quick summary. The sun rains down photons on your panel, knocks electrons loose, the electrons get caught in the junction, your energy flows out of your panel to your charge controller. Your charge controller has been told, or it senses what type of battery you have, so it's charged up your battery as much as it can. Then the DC current flows over to your inverter, it's converted to AC out, you plug your appliances in, and you're happy because you can watch TV during a power outage. So now that I've gone through the basic components and their operation within the system, hopefully I didn't get too technical. It's hard to balance that line between too much and not enough information, right? I wanted to give you the basics of how it actually works and how it flows through the system without getting too technical and going over too many of the nuances and the details of each individual component. But hopefully that gave you a basic idea of how the system operates individually and as a whole. So now let's move on to another whiteboard. This is actually how to properly size / design a small 12 volt solar system. Okay everyone, so here we are. We're going to go over a practical example now and go into a little more detail in regards to how to size your system. You should be familiar with the components now, hopefully. And this is, like I said, a real world example of how to size your system. There are a lot of variables that go into designing and building a system. So this is just one example. Obviously yours may vary. So let's go ahead and get started. This is a sample solar system to run a 5 cubic foot chest freezer 24 hours a day, 7 days a week. A couple disclaimers here. Always oversize your components when possible. There are a lot of variables that go into the operation of a system like this. How much sun you're going to get every day, days without sun, spikes in power, etc. So always oversize the components if you're able to do so within your budget. It's better to have too much than not enough. So also, safety first. Always properly size and fuse your conductors. Very important. You don't want your wires catching fire, so make sure that you properly size them for the amperage they're going to be carrying and to protect your equipment. So when you design and build a system, you don't design and build it from the panels down to your load, whatever you're going to run. You actually design it backwards. So know your load. Best way to do that is to use a kilowatt. This is what I use. So basically, whatever you want to run off of the system, you plug this into the wall as you normally would run it, right into your wall outlet. Then you put the load on here. So if you're running a lamp, you put it on here. You're running a freezer, you put it on here. Whatever you want. And then it actually tells you, it keeps a cumulative record of how many watts it uses. Now, sometimes you can get that information from a tag on the equipment itself or in the owner's manual. That's a way to do it too, but I prefer to use the practical method. Empirical data is always better than something written down, so you know exactly what's going on with it. So that's what I use. And what we want to do, like I said, is we want to know our load. There's 3 aspects to that. You want to know the continuous wattage that it's pulling. You want to know any surge wattage. And surge wattage happens when you have air conditioner, refrigerator, freezer, anything with, like, say, a compressor on it or a motor. It takes an initial surge of amperage and therefore wattage to start that motor going. So say it's 100 watts, the one normally running. It may pull 4 to 5 times that, 400 or 500 watts for a couple seconds to start that motor and then settle back down to the continuous wattage. So you want to know that. And the third thing we want to know is the average watts per hour. And that comes into play in regards to how long you're going to run it. If you're going to run something 24/7, you want to be able to calculate how many watts you need in a day. If you're going to run something 8 hours a day or 10 hours a day, just overnight, say a lamp, then you can plan for that average per day at 10 hours. So once you determine your continuous wattage, your surge wattage, and your average wattage per hour, then you can start actually digging in and doing some of the math. Don't be too scared, it's pretty easy. So, like I said, in this exercise, we're gonna be running a 5 cubic foot freezer. Now, I've already done this, so I know the values here. I use the kilowatt on it. It uses 35 watts continuous. And when the compressor kicks on, it surges up to 400 watts for about 4 or 5 seconds. And if you take the 35 watts over 24 hours a day, because that's what we're going to run it, it's 840 watts per day. Now that we know what we're going to be using, we need to size our inverter properly. Now there's 2 types of inverters. There's pure sine wave and modified sine wave. I don't mess around with modified sine waves anymore. They are less expensive. So if you're limited by your budget, then that works in most cases. But it's better to go pure sine because that's a lot easier on any electronic equipment or anything with a motor. I prefer pure sine inverters because they will run anything you want. So once you pick out the type of inverter that you want to use, then you need to size it properly for your load. Now there's 2 values that you use to size it properly. There's continuous wattage and there's surge wattage. So We have 35 watts continuous that we need to plan for. So I looked online, the best value inverter that I could find that was pure sine wave, 300 watts. That's more than capable of providing our 35 watts continuous power. And that inverter is also capable of 700 watts surge. Now we were hitting 400 watts surge with our freezer, so that's within our parameters, so that should work fine. So you want to make sure that you pick the type of inverter that you want and then properly size it according to the continuous watts and surge watts. As long as they exceed your load continuous wattage and surge wattage, you're fine. And it's also nice to pad your values a little bit just in case something goes wonky over here and you measured something incorrectly, and say that 400 watt surge turns into 600 occasionally because the motor is getting old or something. You want to make sure that your inverter will be able to handle that little bit of extra energy required. Now that we picked out our inverter and we've sized it properly, we need to determine what type of battery we need to run that load. So in this case, batteries are measured in amp hours. So a 12 volt battery at 100 amp hours is approximately 1200 watt hours. Before anybody flames me, I know it's usually 12.8 and the numbers are a little different. I'm just doing this for simple math. So you have a 100 amp hour battery at 12 volts, it gives you approximately 1200 watt hours. There's two types of batteries that you can get these days that are commonly used in solar systems. You have lead acid. Now the limits of lead acid based batteries is you can only use about 50% of their capacity without causing long-term damage to the battery. So if you have 1200 watt hours and a lead acid battery, you can really only safely use 600 watt hours of that before you have to recharge it. If it dips below that on a regular basis, that will kill your battery. It'll shorten the lifespan of your battery. Now the alternate is a Life PO4 lithium-based battery, and that is 100% usable if the battery has a BMS. The BMS is the battery management system, and that will actually cut it off at about 10%, maybe a little under that, to keep the battery healthy. The battery chemistry actually allows you to go down to that 10% with no long-term effects. So once again, lead acid, if you choose that, you get about 50% of the capacity that you can actually use to run anything. That would be 600 in this case, 600 watts. And Life PO4 would be, the full 1200 rated usable watts. So under ideal circumstances, you would get 5 to 6 hours per day offset by your solar input. If you have good sun, then you can subtract that from your 24. That would leave you 18 hours times 35 watts that we know we're running per hour. We're averaging 35 watts per hour, which would equal a need for 630 watts to run that all day, every day. Now, if you use the lead acid, that would be break even. You couldn't have any rain, you couldn't have any cloudy days. You'd have to get that 5 to 6 hours of great sun per day to break even and not go below your 50% where your battery would be damaged. You'd have no extra capacity for a bad day. If you go with a Life PO4 battery, you have enough for your daily operation. And because you can drain that farther, you get more watt hours out of that battery. You'd have one extra day of capacity to pad yourself for rain, cloudy days, etc. Now, obviously, the size of the battery is also based on your comfort level. So, like I said, with lead acid, it would be break even. You couldn't afford to have any bad days or it would damage your battery long term. Life PO4, you have one extra day of capacity, approximately. That's at the 100 amp hour, 12 volt battery. So this is based on your comfort level. If you're more comfortable with more backup time or more standby time, if you have 2 days of snowy weather or 3 days of snowy weather, you want to do the math. So you pump that up to maybe a 200 amp hour or maybe even 300 amp hour to provide yourself that backup power to last you a few extra days to run everything. So as you can see, the advantage here is definitely in the Life PO4 batteries. The cost differential isn't that great. They're lighter, they're safer. It's definitely the way to go. Okay, so now that we've determined our load, picked out our inverter, we've sized our battery for how long we want it to be able to run that with and without any energy coming in, we go to our charge controller and we pick the charge controller. Now what you want to do is you want to ensure that you have enough amperage being output by the charge controller to fill the capacity of your battery in 5 to 6 hours. Have the capacity to fill it from empty to full every day. That's ideally what you'd want if you're running something 24/7. Obviously, these numbers all change. If you want to run something, as I mentioned earlier, for 10 hours overnight or something, then you don't need to fill it every day. You can fill it every 2 or 3 days if you have extra capacity. In this case, we have a 100 amp hour battery. So we'd want, at a minimum, a 20 amp charge controller. That would allow us, within 5 hours of good light, to charge it to full at 100 amp hours. Now, as I mentioned earlier in the video, the charge controller comes in 2 flavors. It comes in a PWM or an MPPT. Now, if you want just a basic system, you're not worried about charging it to full every day, that type of thing, a PWM would be fine. It's a little less expensive. Most of them are solid unless you buy the really cheap ones, directly from China. Sometimes those are a scam, but you can get some legit ones for a decent price. Or you could go for slightly more. You could go with an MPPT these days. The price has actually gone down on them quite a bit. And that would be my preference. I would go with an MPPT because that gives you the most efficient and the fastest charge rate to charge your battery. Okay, we're working our way back here. We've got our load, we picked our inverter, we properly sized our battery, properly sized our charge controller. Now we get to the solar panels. This is where everybody usually starts. But no, we're gonna pick that last because we need to make sure that we have enough solar panels to put enough energy into the charge controller to fill the battery, to power the inverter, to power our load. Now I buy used panels, and the reason I do that is because they're more cost effective. You can typically get a 300 watt plus or minus panel that was decommissioned from a commercial real estate site for about $100 plus or minus 10 bucks, right? So it's a really good deal. The problem with those is they come in different voltages. The majority of them at that wattage are 32, 42 volts, somewhere around there. So you want to make sure that your panel voltage is compatible with your charge controller. If you use a PWM charge controller here, it may be 12 volts only. And you get a 32 volt panel into the 12 volt charge controller, no bueno. That's not good. That's not going to work. So make sure that whatever solar panels you decide to get are compatible with your charge controller. Now, to pick the wattage that you're going to need, you need to provide enough wattage per day to fully charge the battery. So in this case, you need 1200 watts over a 5 to 6 hour period. Remember, that's how much our battery holds. So you want to make sure that you have, over a 5 or 6 hour period, your panels can provide 1200 watts. So that would be, in this case, a minimum of 200 watts. So there's 2 things you want to take into account here, right? The 200 watt rating of your panel is not necessarily going to be that. That is under ideal lab conditions, and when you put it on your roof or put it in your yard, you're going to be lucky to get 160 to 180. So that is one issue with it. The other thing that you need to take into account is that not every day will be a bright, sunny, beautiful day. So that 200 watts is going to be reduced to maybe 180. And then if it's cloudy, you might get 90, you might get 50. So you want to make sure that you add additional panels over the minimum that you require to fill the battery to make sure that you are going to have enough over the course of the day to fill that battery to power that load. So in this case, the minimum would be 200, and that's ideal conditions, which you're never going to achieve. So I would actually double that and go to a 400 watt minimum. All right, everyone, I hope that wasn't too convoluted. I hope maybe you gained some knowledge off of that. If not, you can hit me up with questions in the comments. I do have a full-time job, but I try to do my best to answer as I go. If you're still on the fence about actually designing and doing it yourself, then on my website, thetechieprepper.com, if you look under the solar freezer section, you'll see that I do have a very basic line drawing / schematic that details all the fuse sizes, all the wire gauge sizes and everything. So that could help you as well. Additionally, in the description section below, I will put a complete parts list down there. They are Amazon affiliate links. I'd appreciate it if you do use them because it will help me out. And I promise any money I make off of those links, I will put back into this channel 100%. I do have a full-time job, but that would allow me to buy more things to show you. So that's kind of cool. So if you learned something today, please like the video. Please subscribe so you'll know when I have new videos coming out. And most importantly, like I said, I do this to help people. So if there's somebody that you know or love that could use this information, please by all means share it with them. And I will see you next time. Bye.